Hello, everyone. First of all, I would like to thank the organizers for the space. My name is David Raudales, and I'm a second-year graduate student at Georgia Tech. I come today on behalf of the Trinity collaboration to share a very exciting update on our experiment, the Trinity Neutrino Observatory, which consists of an array of imaging air Cherenkov telescopes like the one you see in the slide here. And we basically aim to see at very high energy astrophysical neutrinos from 1 PeV to 10 eV. And let's start by talking about why these neutrinos are important and how they're produced. And the production mechanism basically involves ultra-high energy cosmic rays that interact with either a photon target or some proton target. And from this photohadronic or hadronic interaction, you can get either a neutral pion that then further decays into gamma rays, or you can also get a charged pion, which then further decays into neutrinos. So this production mechanism is interesting because from the same production mechanism, you get three messengers, each of them with advantages and disadvantages. But we care specifically about neutrinos right now. So these neutrinos don't get deflected by magnetic fields like cosmic rays do. So then they point straight back to their sources. And also, they basically come with the same energy as they're produced because they don't get absorbed and re-emitted in the universe, as opposed to gamma rays. So then these neutrinos gives us a very good way of resolving these high energy sources. Now, what makes these neutrinos strong also makes them very hard to detect because they almost don't interact. And a lot of the future of these neutrino experiments is just try to have a very big fiducial volume for these neutrinos to interact. This is where the Trinity approach comes in. So the idea is to take your Cherenkov telescope and point it down to the horizon such that you use all of the Earth's crust, or at least, well, a good portion of the Earth's crust as your fiducial volume. So the way this works is a neutrino comes in at very shallow angles, like you see here, and then with some probability, it would interact with a charge current interaction and further produce a tau lepton that would, with some probability, exit the Earth and then decay into a particle shower. And then the charged particles in this particle shower, as they move through the atmosphere, they emit Cherenkov light that you can collect with the mirrors of your Cherenkov telescope and then focus it into a silicon PM camera that allows you to image the shower. This technique has been used widely for gamma ray observations, which means that we know pretty well the technology. Okay, and this technique has actually been tried before, and one of the attempts was done by the MAGIC collaboration, which is an array of two of these Cherenkov telescopes meant for gamma rays. And the MAGIC collaboration basically decided to look for these Earth-skimming neutrinos by tilting their telescopes down to the sea. And they didn't see anything, but with 30 hours of observations, they could place upper limits. And basically, they realized that they were not able to have competitive sensitivity to other neutrino experiments. So they just stopped the observations. And you might be asking if the upper limits for MAGIC are not good, what's the difference between MAGIC and Trinity? And you can see that from this image here. And basically, the MAGIC field of view is too small. So then the fiducial volume that you cover with MAGIC was also too small. And the idea behind Trinity is you want to build an imaging Cherenkov telescope that has a very wide horizontal field of view, such that you maximize the fiducial volume that you cover. And of course, to understand the importance of Trinity, it's important to understand what's the landscape for neutrino experiments. And so far, in the high energy neutrino window, IceCube has seen a diffuse astrophysical neutrino flux all the way to some PeVs in energy. And then some experiments have placed upper limits in the ultra high energy neutrino range. Now, the problem is these upper limits usually go well above the projected fluxes of neutrinos. Now, new techniques are shown here with the dashed lines, and I also show them in the right with a little cartoon here. And there's a lot of things that are being explored. One of them is experiments looking at valleys and mountains, like the ones you see here. Then you have experiments that are more IceCube-like, that are embedded in a medium. And then you also have balloon and satellite missions. Of course, each of these experiments have different advantages and disadvantages, but I want to show you something. And what I want to show is the different energy ranges that these experiments cover. Radio experiments, for example, which look at Ascarian radiation, which is a radio signal that comes from the air showers. have good sensitivity from around 100 PeV to 10 EeV, or they could go even to higher energies, as you can see with some of them here. And also, ice and water Cherenkov telescopes have good sensitivity at the lower energy part, or all the way to like, I would say 10 PeV. But then we have a little bit of an energy gap here, and this is what the imaging Cherenkov technique closes. And this gap is particularly important because it's where we have the transition from astrophysical neutrinos to cosmogenic neutrinos. So then if you want to characterize the tail of the astrophysical neutrino flux, it's essential that we have good sensitivity in this energy range. Moreover, the Trinity experiment low energy tail overlaps with the high energy tail of the diffuse flux of ice cube. This basically means that we have ensured neutrino detection, at least at these lower energies. Now I want to focus a little bit on what have we done, where are we now, and where are we going. And for this, it's very important to understand that Trinity is being built in three stages. I'm going to focus on the first stage now, and we will talk about the other two later. So the first stage that we call the Trinity Demonstrator, it's a relatively small 1 square meter telescope. It has around a 4 by 4 degree field of view and a 0.24 angular resolution, has been taking data since October 2023, and is now fully commissioned. So the main objective of the demonstrator is to study the background, test the camera technology, and test the remote operations. It is located in Frisco Peak in Utah, and this is what you can see here. This red square shows you here what's the field of view of a telescope, and you can always see the horizon view from our camera that's in the Trinity Observatory. You can actually always see the telescope live from the Trinity Observatory website. So as I was mentioning, the commissioning phase is now done, and we have a commissioning paper out that you can go check. And one of the cool things that we did during commissioning was basically taking the telescope and making it point up, such that we can see Cherenkov light from cosmic ray showers. So when we did this, we could actually see these cosmic ray images, and we didn't do much with them other than just saying that we're able to look at these cosmic ray showers. Uh, and of course, after taking data for now more than 2 years, we are going into our first data analysis runs. So the data set that I'm going to cover right now, it's composed of 346 hours that were taken between October 2024 and June of 2025. And it's composed of a total of more than 1 million events that trigger the camera readout. And now this is not all of our data, but it is the best data that we have from this period. And we're still working in analyzing all of the rest of the data. So the trigger condition for the camera readout, is that 1 pixel goes above 20 photoelectrons, and this means an average trigger rate of 0.5 events per second. Of course, we need to take all of this triggered events through an event cleaning algorithm, which is composed of a core and boundary pixel selection method, which has been used before by gamma ray telescopes for cleaning gamma ray images. So here in the left, you can see a simulated gold-plated event. And this is a very highly energetic neutrino air shower from a 400 PeV neutrino, and it's also very far away at around 170 kilometers. And this is how this simulated event would look like in our camera. So this is the simulated camera response. And be careful with the color bars here because one is in photons and the other one's in photoelectrons. But what you can see here is all of these yellow squares are because of how our saturation is set are 160 photoelectrons. So of course, saturation is something that we're also studying. But for the purpose of this, we are going to treat it as 160 photoelectrons. So first of all, we want to look at our core pixels. And these pixels are pixels that are neighbors to the pixel that triggered and are within some dynamical range. And then the resulting core pixels are the ones that you see here in black. And from this, we can get our boundary pixels that are basically pixels that are next to a core pixel and that are within 30% of the maximum triggered pixel. And after this, you get your cleaned band, which looks something like this. So after we pass our data set to our event cleaning algorithm, we get around 497 events. And we want to parameterize this in some way. So for this, we use these two parameters, image pixels and size. So the image pixels is just the total amount of pixels in the cleaned image, and the size is just the total amount of photo electrons in the cleaned image. So when we plot this, it looks something like this. And you can see that events are mostly clustered at small sizes and small image pixels. And now, if you were to see this gold-plated event, it's located somewhere around here. Of course, this is a relatively energetic, relatively far away event, so then it doesn't mean that all of the neutrino showers are around here. This is just here just for reference. Now, when we look at the data set, we can classify our events in four types. And I like to call this event taxonomy, and I'm actually going to go one by one in each of these. So the most common of these are muon tracks, which turns to be around 1 event per hour. And the reason why we initially thought these were muons is because you can basically uh, track a line in each of these events, which is basically a good indicator that you can have a muon going through the camera ionizing the silicon PMs. Of course, we tested this further by placing scintillator paddles uh, on top and at the bottom of the camera. And then when the scintillator paddle triggered, we would also look at the image from the camera. And then with this, we could actually see these muon tracks pretty well using these scintillator paddles. Now, for future experiments, for the future stages of Trinity, we can just put permanent scintillator paddles, which would avoid these muons, and basically makes us being able to completely, ruled out this as possible neutrino events. Now, the other one, spillovers. And these spillovers, we think that are the result of delta rays that just, you have a charged particle coming into your camera and then it knocks out an electron and the electron ionizes the material in the camera. And then you see these sort of spillover events. We also have what we call fuzzy events, and these were one of the toughest ones. They're not that common. It's only one event every 173 hours, so we only have two in the whole data set. But it was hard to sort of realize what these were until we started doing muon simulations to study the muon background. And um, we realized that a muon going almost head onto the camera would produce a signal that's actually very similar to these fuzzy events. So now we think that these fuzzy events are actually just muons as well. Another type of event that we have is just a camera module glitching. And this is our camera, and you can see that we have these pixel matrices here, and each of these is connected to this board called SIAB. So basically, this is just electronic noise, and you can see that very clearly because it's the whole SIAB that's glitching. So you can very clearly see that this is not a neutrino air shower. So mainly what I want you to take from this is that our experiment is background free because we're able to characterize pretty well all of these events as not being neutrino events. And these are all of the events that we see. So we claim that our experiment is background free, at least with the dataset that we have so far. So now that we know that we have a background-free experiment, we're ready to move to the next stage of Trinity, which is the first full-size telescope, Trinity One. So this telescope is way bigger than the demonstrator. It's 16 times bigger, and it has a way wider field of view of 60 degrees in the horizontal. Now, the construction will depend on funding, and we're currently looking for funding from Trinity One. But once Trinity One is fully commissioned, we're going to move towards the full Trinity Observatory, which is an array of 18 telescopes like Trinity One, distributed in 3 sites, such that you have 6 telescopes in each side, covering a whole 360-degree field of view. So if the experiment is background free, then you expect to see a linear increase in diffuse flux sensitivity with the number of telescopes. And you can see this in this plot here, in which with each stage of Trinity, you have around an order of magnitude increase in sensitivity. Now, right now, I'm mainly going to focus on our recent performance studies for Trinity One. And first of all, I want to show you the effective area. So here you can see the simulated effective areas for a 60-degree horizontal field of view telescope to 1 eV and 1 PeV neutrinos. And if you look at the right here, you can see the all flavor direction averaged effective area. And what's interesting to note is that From 10 PeV and above, Trinity One overcomes the ice cube effective area. So Trinity is way more sensitive. Trinity One is more sensitive at higher energies. Now, once you have your effective area, you want to look how sensitive you are to look at short bursts. And by this, I mean bursts that fall completely within your field of view. And the usual standard for this is around 1,000 seconds, which is around 16 minutes. But what I want you to see from this plot mainly is how a single Trinity One telescope has already comparable sensitivity to these short bursts to 100 stations of a radio experiment like Beacon. And then you can also see that our energy range is pretty ideal for constraining GRB models, which is what is being shown here with these dashed lines. And transient sources are going to be one of our strong science cases, as I'm going to try to mention in a bit. And another thing that's cool about Trinity One is that it's going to be able to repoint, so rotate in azimuth. And here I am showing the accessible effective area considering rotations with Trinity One. And when you evolve this accessible effective area over a day, you get basically your accessible sky over a day and what we called our daily averaged effective area. So this considers only an 8-hour night because we're only able to observe in the night and under certain illumination conditions, but it's averaged over a full day. And with this daily average effective area, you can get your long burst sensitivity. And what you can see here from this plot is that, again, you're in a very good energy range, but also you have comparable long burst sensitivity to 1,000 stations of a radio experiment like Beacon. And again, this is for sources that are more than 1,000 seconds. Then we also have our acceptance, which is basically integrating our effective area over time and weighting it with a e to the minus 2 spectrum. And this basically already takes into account the necessary illumination conditions for you to observe each of these points. And what we find when you calculate this over a year, it's that around a year we have approximately a 20% duty cycle. So now, what can we expect in terms of transients? I think that's very interesting. And one of the things that we wanted to look at is what's the probability of us observing a boat like GRB, so a very energetic GRB like the brightest of all time, if it were to fall within our field of view. So this is considering an internal shock model, and you can see all the way to 61 neutrinos. And then if you want to quantify how far away you can see these sources, you can do some statistics, and then you get the probability of looking more than one event for a given luminosity distance. And you can see that even for 100 megaparsecs, you still have a very good probability of detecting a boat like GRB. So this is basically the whole universe. Now, something that's more common, like a short GRB, you would expect to see a maximum of 26 events at 40 megaparsecs, and you can see that your horizon is actually further away than a radio array like IceCube Gen 2 radio, following the same statistical argument. So, take home messages. We have our first data analysis run, and everything points to a background-free experiment. Um, we are working towards Monte Carlo-based discrimination and event selection, using neural networks. And Trinity is an experiment that has pretty good transient source sensitivity. And with the ability to rotate in azimuth, it has pretty good follow-up potential. And then we are working towards limits on the diffuse neutrino flux and also some some Poisson's emissions constraints with the demonstrator. And we're also working pretty hard towards a strong science case. So we're working in prospects for astrophysical and neutrino physics. So stay tuned for all of the results in the future. Thank you for listening.